Okay, this week's videos are about other specific uses for the chi-square distribution. So far, we've only used this distribution for one sample variance test, but it is far more useful than just that. And the chi-square tests that you see this week are very commonly used in statistical analysis. The first chi-square test we'll look at is called the goodness of fit test. This is the extension of the one sample z-test for proportions. The difference is that the z-test applies to binomial variables that have only two categories, while this chi-squared test applies to multinomial variables with more than two categories. For notation, we'll call the number of categories k. The basic process is the same. We'll sample n random subjects and count how many fall into each category. These totals are called the observed values. And each category also has an expected value that is based on the null hypothesis. The chi-squared formula is based on these observed and expected values. O stands for observed and E stands for expected, and it has k minus 1 degrees of freedom. Our first example is about fast food market share, and there are four categories: McDonald's, KFC, Burger King, and other. The null hypothesis is given in the question, and it has to specify the proportion or probability for each category. And of course, these proportions all must add up to 1. And the alternative hypothesis is that the distribution of proportions is something else. And we're testing this hypothesis at 5% level. After observing 300 random people, we get these results. These are the observed values. Next, we need to calculate the expected values, and we use this formula. For each category, we multiply the sample size by its proportion from the null hypothesis. And that results in these four expected values. Let's plug these numbers into the chi-square formula. We have four categories, so there are four terms in the sum. For each category, we plug in O, the observed value, and E, the expected value. And here's the full calculation. The first term represents McDonald's. The second term is KFC, and so on. The numbers work out like this, and they all add up to 15.5 with 3 degrees of freedom. Let's look at the chi-square distribution with 3 degrees of freedom. Much like ANOVA, this test is always one tail, right tail. So with 5% level, the critical value for rejection is the point that has an area of 0.05 to the right of it. And with 3 degrees of freedom, that critical value is 7.81. Our chi-square value of 15.5 is beyond the critical value, so we would reject the null hypothesis and conclude that the market share for fast food has changed. And to get a sense of exactly how it has changed, we can look back at the calculation. The largest contributions to the sum reflect categories where the observed values are relatively far away from the expected value. Since the other category is the major contributor to the chi-squared sum, we can infer that its market share has changed the most. There's one more thing I want to point out in the calculation. The KFC part of the calculation came out as 0, since the observed and expected values were exactly the same. This helps explain why the chi-square test is one-tailed. Small chi-squared values mean that observed values are relatively close to their expected values, and that is strong evidence in favor of the null hypothesis. We would only reject if observed values are relatively far from their expected values, which would lead to a large chi-squared value. Much like the one-sample z-test for proportions, the chi-square is only an approximation of the distribution. We need a large sample size in order for the central limit theorem to kick in and make the approximation close enough. The rule of thumb for sample size is that the expected value for each category should be at least 5. That is the bare minimum requirement. And of course, as the sample size increases, the approximation becomes even better. Okay, the next example is about rolling dice in a casino. In the game of craps, you roll 2 dice and add them up. And there are 3 outcomes of interest in the game. A natural, which is 7 or 11, craps, which is 2, 3, or 12, and then all other outcomes, which are 4, 5, 6, 8, 9, or 10. We're going to test whether the dice are fair or not at 5% level. So we're going to assume in the null hypothesis that they are fair. You surely studied probabilities for fair dice in IntroStat, so you should be able to calculate the probability of a natural is 2/9. The probability of craps is 1/9. And the probability of all other outcomes is 2/3. The observed values were given in the question, and here they are. The expected values are calculated by multiplying sample size times each outcome's probability. We can plug in the observed and expected values into the chi-square formula. Since there were 3 categories, there will be 3 terms in the sum. And here is the full calculation. It all adds up to 4.75 with 2 degrees of freedom. And if we look at the chi-square distribution with 2 degrees of freedom, then the 5% critical value is 5.99. Since our chi-square value is less than the critical value, we would not reject. What does that say about the dice? The null hypothesis was that the dice are fair, so not rejecting leads us to the conclusion that the dice are fair. Actually, it's more appropriate to say that we don't have enough evidence to prove that they are unfair. If you have noticed, I don't like to say that we accept the null hypothesis. I prefer to say we did not reject the null hypothesis. What's the difference? In this problem, if you say accept the null hypothesis, then you are implying that you believe the dice are fair. If you say did not reject the null hypothesis, then you are saying that we were unable to prove the dice are unfair. Logically, they are equivalent, but the words don't quite mean the same thing. Saying that the dice are fair is not quite the same as saying that we couldn't prove they are unfair. Anyway, you now have 3 problems coming up to do on your own. Good luck with that, and check out the next video.